Okay, so now let's do the rest of the exercises. So question number 7. Indicate the order of priorities and stereochemistry of the molecule shown below. So again, by showing your work, that means you will be showing which substituent is priority 1, priority 2, 3, and 4. And then stereochemistry, whether this molecule is R or S. And so we have here actually an amine with, of course, hydrogen and two substituents. We have triple bond and double bond. So it's easy to determine order of priority of substituents 1 and 4. Amino group, nitrogen, has higher priority than any other atom bonded to chirality center. That's priority 1. And hydrogen, as usual, the lowest priority. The only time where it's a little bit complex, a little bit changing, is if none of the substituents is hydrogen. Then, of course, you have to figure out which has the lowest priority. Now we have two carbons of the same priority, and we have carbon-carbon triple and double bond. We have to figure out which substituent has higher priority, so you need to add virtual atoms. Since these are carbon-carbon multiple bonds, all the virtual atoms will be carbons. So for triple bond, we are converting carbon-carbon triple bond to, with respect to each carbon atom, to three carbon-carbon single bonds. So there is one existing carbon-carbon single bonds left over from triple bond, and you are adding two more virtual bonds and virtual atoms for each carbon atom, one existing and two more. For double bond, you're converting double bond into two carbon-carbon single bonds with respect to each carbon atom. And so which one is higher priority? So carbon versus carbon, that's a tie. Then again, carbon versus carbon, it's a tie. In each case, you follow path of highest priority. And then we have virtual carbon versus virtual carbon. That's still a tie, and we have reached the end. So what that means is that following path of highest priority, we have reached the end, and it's a tie. So we follow path of second highest priority. So in this case, if this was path of highest priority, carbon, 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 path of second highest priority is going to be again carbon, carbon, the other carbon. So this third. But here it's going to be carbon, carbon. We already took this carbon was used in the first path. It's going to be hydrogen. So virtual carbon versus hydrogen. Carbon has higher priority. So this entire substituent triple bond has higher priority. And that's shown here. So you see path of highest priority in red versus green. Tie. Second highest priority in blue versus purple. And now you can see top substituent, what used to be triple bond, higher priority. And now that you have priorities identified, this is perspective drawing. A previous example had Fischer projection, and to determine whether configuration is R or S, you would place lowest priority substituent on vertical bond. And then you determine whether one, and then you ignore it, and you determine whether substituents of priority 1, 2, 3 are in clockwise or counterclockwise array. Or for you, it's the opposite, like clockwise and counterclockwise. We are watching mirror image of each other. So for perspective drawing, there is only one substituent at the back, one on the dashed bond. So you have to send the lowest priority substituent, priority 4, to the dashed bond. The easiest way to do it is to flip position of two substituents in pairs. So you flip that one with something else. So let's say you flip 1 and 4. So amino group and hydrogen. That way hydrogen is at the back, amino at the front. But to keep it the same enantiomer, you have to flip the other two. So you have to flip 2 and 3. And now you can ignore hydrogen. And so 1, 2, 3 is counterclockwise or S. And so your answer would be, actually I didn't type it here, let's see. So on the test, you will type your answer like this. Okay, it's triple bond. I will have to insert here triple bond. I don't know how you do it on the test. Oh, here is how you do it on the test. Okay, you put double bond and then you underline it. Let's see. Hopefully well, that's not the way to underline. Yeah, I don't need to underline this carbon. So it may not look like triple bond, but underline double bond would be triple bond. There is a symbol for triple bond, and then and actually it should be CH. And for is H. And then again, this S doesn't have to be italics. So this would be complete answer. Complete answer showing your work. So this means showing your work. And of course, since we have CH versus CH2, I would recognize double or versus triple in case there are some problems with font. But this is how you do when you're typing. Yeah, it's good to have this question. So if you have to type triple bond, that's how you would do it on the test. There is a symbol in Word to insert triple bond. If you go under insert and there is a symbol for triple bond. That's mathematical identity sign. But on the test, underlined double bond means triple bond. Actually, let me see if there are any questions before we move on to 8. No. So, how many isomers of 2,3 dimethoxybutane, not methoxy, 2,3 dimethoxybutane are possible? Okay, so what you would do is you would make 2,3 dimethoxybutane. So maybe you can also draw a formula, and from a formula you can see it. So you can make a model or draw a formula. If you are particularly Fischer projections are really good at it. But anyway, if you make a formula, if you make a model, so 4 carbons is butane. So this is butane, 4 carbons. And 2,3-dimethoxy, you can simply put 2 oxygens. Red is oxygen. On carbon 2 and carbon 3. And then you look how many isomers you would have. Actually, you would be making all the models. There are actually 4 different models you can make. In Fischer projection, if you recall, that's actually small animal convention. If you imagine somebody throwing small animal at you, this would be its legs or projecting towards you, like that. See, so this is in the plane of the drawing. These 4 legs projecting towards you. This is head and tail away from you. So obviously this would be one enantiomer, and then we can make another one. But to figure out all of the isomers, if you flip, see just one, you end up with what is called a Miso compound. This is chirality center, and this is chirality center. But you see, this molecule is symmetrical. See plane of symmetry right here. This is symmetrical molecule. If you flip it to 180, that's actually identical molecule. And it looks like 180 flip is allowed. So when you flip formula 180, you get the same molecule. But when you flip it to 180, I don't have enough atoms here. Actually, I can break this 6-membered ring. I probably won't need it. It's a good idea if you know this before the exam and you don't need to use models, because this could take a while if you're using models. See, when you make two mirror images like this, they actually superimpose one on the other, which means compound is identical. This means superimposed, they overlap. And that's how it's superimposed. So this is actually Miso. Or even better, you simply draw a Fischer projection. That's why Fischer projections are great. Because if you draw a Fischer projection, this is butane. A methyl group, CH2, CH2, methyl. So if these were hydrogens, both hydrogens, this would be butane. So 2,3 dimethoxy, you place methoxy group on each. Yeah, so this is 2,3. You see, this one has plane of symmetry going through the middle of the molecule. Reflects one half of the molecule into the other half. That's plane of symmetry. And that means that it has Miso isomer. Compound that has chirality centers, but is not chiral itself because of the presence of symmetry, of plane of symmetry. And so in case of Miso isomer, what would have been two enantiomers, they are identical. It's the same molecule. While in pair of enantiomers, RS pair of enantiomers, RR or SS pair of enantiomers, see, these are two mirror images. And they are not superimposable. See, if you try to superimpose them, it doesn't work. Hydrogen and oxygen are overlapping, so that's wrong. And if you try to flip 180, you still end up with the same problem. They are obviously mirror images and enantiomers of each other. So we have a total of 3 isomers. We have pair of enantiomers, that's 2, and Miso third. So that's the case of symmetry, where due to presence of symmetry, instead of 4 possible enantiomers or 4 possible stereoisomers, 2 pairs of enantiomers, we have only 1 pair of enantiomers and Miso isomer. So always watch for that. Not to avoid having Miso isomer, symmetry would have to be broken in molecule. Somehow we would need another substituent somewhere else so that these two substituents are not identical, these two at the end. That's similar to situation with double bonds. Remember, if you have two double bonds, EZ and ZE isomer were identical if molecule is symmetrical. And if there is something to break that symmetry, then EZ and ZE isomer are different. So with two double bonds, we could have 3 or 4. If both double bonds exhibit isomerism, we could have 3 or 4 isomers, depending on symmetry. If symmetry is present, only 3. If it's not, 4. So here, it's the same situation with chirality centers. Just now, instead of double bonds, we are looking at chirality centers. And if symmetry is present in the molecule, then that eliminates one of the isomers. Basically, RS is identical to SR. So pair of enantiomers would be RRSS, while Miso is always RS or SR. And that brings us to the next question, number 9. Which of the following is a Miso isomer? And sometimes some standardized exams like MCAT will ask questions like this, and students would go and work through it, trying to figure out which one is Miso, making these models or drawing them. Or actually, you're not allowed to make models, but trying to figure that out. But actually, I just told you what is Miso isomer, RS. Miso isomer is always RS or SR. RRSS, SSRR. Actually, so yeah. SSRR, those are enantiomers. So one of these is RR and SS, and another is SS. I don't know which is which. I could figure it out, but this one is RS. That's for sure. Now here we have 2,3 dibromo. I'm missing this di. Okay, I'll fix everything in file. Dibromohexane. Now 2-bromo-3-hexanol. This one has no Miso isomer because 2-bromo-3-hexanol is not symmetrical molecule. This 3-hexanol that breaks the symmetry. All substituents must be identical. So substituents have to be, you see, on this chirality center, substituent is hydrogen, in this case methoxy and methyl, and this group. On the other one, hydrogen, methoxy, methyl, and this same group. So each chirality center has the same set of substituents. That makes it Miso. That makes possibility for Miso isomer. And then if it's RS or SR, that's Miso isomer. But if you have 2 bromo 3 hexanol, there will be 2 more carbons, but one would be bromo, one would be hydroxyl. So they are different, and 2 bromo 3 hexanol actually has 4 different isomers, because Miso isomer in case of 2 bromo 3 hexanol does not exist. Okay, so let's see if there are any questions. Okay, no questions. Either this is really easy, you all figured it out, or you have no clue what I'm talking about. So either way, you have no questions. So question number 10. The following formulas represent. And so A, if you have choices, we can just go with A to discuss them a little bit. 2 identical molecules, but not Miso isomer, and pair of enantiomers, for example. Well, if you have just one chirality center, and that's the case A. If you have one chirality center, there are only 2 possibilities when you're given 2 formulas. Either those 2 are pair of enantiomers, or they are identical, 2 identical molecules. They cannot be anything else. They cannot be Miso. They cannot be also erythro-trio pair of enantiomers. Nothing like that. By the way, erythro and trio, in Fischer projection, B would be erythro. If identical substituents are on the same side in Fischer projections, that's erythro, like this. That's erythro pair of erythro pair, actually it's Miso. And this, when they are on the opposite sides, that's trio. But for that, you need 2 chirality centers. So if it's one chirality center, there are only 2 possibilities, either identicals or pair of enantiomers. And so 2 identical molecules, but not Miso isomer, that's a possibility. Now, how do you figure out whether they are identical? There are several ways to do it. One is to determine RS configuration. So determine whether this is R or S, is this R or S, and then if they're both R, both S, they're identical. If one is R, the other S, they're pair of enantiomers. Another is to make models. So from each of these molecules, you make models and compare them. Are they mirror images, pair of enantiomers, or do they superimpose? Are they identical? And third possibility is shown here. You carry out allowed transformations of a formula. So you keep one formula where it is. See, the same, one on the right. But one on the left, we are going to flip substituents. So you see here in formula on the right, hydrogen is on the top. So you flip hydrogen and methyl to keep hydrogen on the top. But to keep it the same enantiomer, you have to flip the other 2. Remember, that's allowed transformation. You can flip position of any 2 substituents as long as at the same time you flip the other 2. And so you flip hydrogen and methyl, but you have to flip nitrogen and oxygen. But still, you may not be able to compare them. Now, you may want to flip, in this case, let's see, what did I do? I redrew this one so you can see these 2. So I redrew A so that you can compare them more easily. So now when you look at them, you can see they are mirror images of each other, and that's beauty of Fischer projections. When they are mirror images in Fischer projection, that means they are enantiomers. They are really mirror images in 3 dimensions. So in this case, just this one transformation. Sometimes you may have to do more than one transformation, but in this case, just this one transformation did it. So sometimes you may have to flip one and then do some flipping on the other and so on. Okay, now you did it. And they are mirror images of each other, so they are enantiomers. And so A is not correct because they are enantiomers, so B, C, or D must be correct. And now choice A. Now you move to pair B. So what is pair B? Pair of diastereomers. Diastereomers would be compounds that are stereoisomers but not mirror images of each other. So like erythro and trio. Like when two substituents are on the same side and in the other compound, they're on the opposite sides. They're not mirror images of each other, but so that's not the case. Two molecules of Miso compound. That's actually exactly what it looks like, because there is, if you do 180 degrees rotation, you go from one to the other. And 180 degrees rotation is allowed transformation of Fischer projection. That means you get, when you do 180 degrees rotation, it's the same molecule. And so if you can convert one into the other by 180 degrees rotation, that's it, that's the same molecule. So they are identical. And that's Miso compound because while they are identical, two mirror images are identical, there are individual chirality centers. Each compound has two chirality centers. And that's the definition of Miso compound. Compound that has chirality centers, but is not chiral itself. Overall molecule is not chiral itself. So, because chirality is property of the entire molecule, not individual atom. So C is correct. And D is not correct, obviously identical. So make sure that you distinguish between identical and Miso, because identical molecules do not have chirality centers. So for example, if two substituents were identical, then that would not be a chirality center. Like here, the substituents were identical, like on chirality centers. So this is Miso isomer, C. So if you have two chirality centers, possibilities are that you have two identical molecules. Actually, sorry, with two chirality centers, you can't have two identical molecules. If you have chirality centers, then it has to, if it's not chiral, it has to be Miso. So with two or more chirality centers, unlikely we'll have more than two. With two chirality centers, possibilities are that they are pair of enantiomers, if they're simply mirror images of each other. Miso, if you have chirality centers, but overall molecule is not chiral. You can find plane of symmetry, or flipping one into the other, 180 degrees flip gives you the other, that's Miso. And third possibility is pair of diastereomers, and diastereomers would be like erythro trio, substituents on the same side or the opposite sides in Fischer projection. While with one chirality center, you have only two possibilities. Identical molecules, but not a Miso. With one chirality center, it cannot possibly be Miso. You need minimum of two. So either identical molecules or pair of enantiomers. Okay. And we have one more question, then I will stop recording. So if you have anything to ask, you can ask at that time. So a sample of plus menthol has optical purity of 40%. What is the content of plus, not limonene, but menthol, of plus menthol in the sample? So if you have optically pure material, you could have pure enantiomer, and those enantiomers are designated by sign of rotation. Plus rotates plane of polarized light clockwise, minus counterclockwise. If enantiomer is pure, then it's 100% pure. It's just one enantiomer, and it's only that enantiomer that rotates plane of polarized light. And so plus menthol will rotate plane of polarized light to the right, minus menthol to the left. And each of them will rotate plane of polarized light by certain number of degrees, same number of degrees, to the right or to the left, depending on which enantiomer it is. Another possibility is that we have mixture of two enantiomers. And if they are mixed in equal amounts, 50% plus, 50% minus, then since they rotate by exactly the same amount to the right or to the left, then plus menthol will rotate to the right, plane of polarized light to the right, by certain amount, and minus to the left by exactly the same amount. And since they are 50-50, they will completely compensate each other, and there will be no net overall rotation. That's racemic mixture. So racemic mixture is a mixture of 50% of plus and 50% of minus enantiomer. So it's mixture of equal amounts of the two enantiomers. So those are two extremes, having pure enantiomer or racemic mixture. But we can have anything in between. And for mixture that is anything in between, then we express that composition as optical purity. And optical purity is basically a component that causes rotation of the plane of polarized light. That's the amount that is in excess. In excess, and rest is racemic mixture. So when we say that plus menthol has optical purity of 40%, that means out of 100%, 40% is excess of plus menthol. And those 40% rotate plane of polarized light or cause plane of polarized light to rotate. Remaining 60% does not rotate plane of polarized light. That's because those 60% are racemic mixture. And racemic mixture is half plus, half minus. So those 60%, that means 30% plus, 30% minus. And so if you are looking for total amount of plus menthol, it's going to be 40% that it is in excess, plus another 30% that is part of the racemic mixture, total of 70%. So that's correct answer. Read question carefully. If you get question like this on the test, read very carefully what you are being asked. So is it the same enantiomer that is in excess? Because if plus menthol has optical purity of 40%, that means it's 40% in excess above the racemic mixture. Is it the same enantiomer or is it the other enantiomer? Because obviously I could have asked what was the content of minus menthol, so the minor component. And then minor component will be only half the racemic mixture. So if optical purity is 40%, racemic mixture is 60, minor component is half of that, 30. So question could have been, what is the amount of minus? So read very carefully. Are you being asked about major component, when it is in excess, that is represented by optical purity, or minor component? Okay, and so that's it. That completes exercises for chapter 11. I will stop recording now, and then if you have any questions, you can ask your questions.